All right, hello and welcome to Lab 4. This one is all about relations. So we're going to get some practice with encoding relations inside of a computer. So we're going to model relations as you normally do as a set of pairs of what is related to what. And to keep it simple on ourselves, we're going to make a set of pairs of ints. Okay? So every relation is going to look like this. It's going to be a set of pairs of two ints. It's like the first thing is related to the second thing. And we're just going to use numbers to say what's related to what. All right? So let's get an example with an injective function. All right? It's a function that is injective one-to-one. And the domain of all these, because of the way I'm defining it inside of the lab, the domain of any injective function is just going to be implicit. It's just all the things that are being taken somewhere. All right? So I'm using ints, like I'm not giving a corresponding value to every possible integer. It's just the ones that are given. Assume that that is the entire domain. This will make sense when I give you an example. So here's that example. An injective function could look like this. It's like, I have to give numbers to specify what these dots mean, but let's say they're numbers, and like I'll label them like this: 1 and then 3 and then 5, and 2, 4, 6, and I don't know, this one could be 7 just for fun. And so this is a function if it's one-to-one. Like this value is not going two places, it's just going one place. It's like 1 maps to 2, 3 maps to 6, 5 can map to 7, I guess. And you can represent this with a relation that represents the function, right? So it's like 1 then 2. 1 is the domain, 1 is the input, 2 is the output of the function, right? So that's the arrow relationship. It's like the source of the arrow, the target of the arrow. That's the order. Order is important. Then we have 3 and 6 are related under this function relationship. And then 5 and 7 are related. All right? And that is an injective function. And you can just assume implicitly, like, all the things on the left-hand side, those are the entire domain. Okay? So you don't have to check, like, everybody in the domain is being mapped to somewhere in your code. You can just assume, like, all right, everybody here, that is my entire domain. I'm not missing anybody. Okay? So that's how you can model, and obviously you can translate this into a set of pairs in C++. Not too bad. Yeah. So that's my first example. Let's have another example with a symmetric relation, a relation that must be symmetric. And again, we're going to label each thing that can be related. Our set of things is just numbers. So let's label all these with numbers. 1, just to keep it easier on ourselves for the implementation. 4, 5, and 6, and let's assume this is a symmetric relation. So if I know that 1 is related to 2, it must be the case that 2 is related to 1. All right? If I know that 2 is related to 5, it must be the case that 5 is related to 2. And same for these guys. So this is a symmetric relation. I hope you can see. These guys are just lonely, but it doesn't make it a non-symmetric relation. It just means they're not touching anybody. They're not related to anybody at all. But if there is a relationship, you must be able to reverse that arrow. All right? So this can be R2. And again, we can represent this relation as a set of pairs with integers, because those are the labels here. So 1 is related to 2, that's this top arrow. And because it's symmetric, we know that 2 is related to 1 as well. So we have the bottom one. 2, 1. And then we know 2 is related to 5, and then also 5 is related to 2. Do you see how you can kind of check that it's a symmetric relationship somehow? See a pattern going on here? And then if I have 5, 6, because it's symmetric, I also have 6, 5. That's the kind of code you're going to think about writing. Yeah. So that's how you can represent this relation inside of a computer. Okay. So with that, let's talk about the write-up. This lab will be due week 14, by the way, so plenty of time to do it. And yeah, it's about relations. So here are all the files you'll get. You're going to implement the relation class, all right, inside of relation.cpp. So I've given you relation.h with like the scaffolding for everything, and then you're going to implement all the stuff in relation.cpp. All right, the things that are being related to each other are just numbers. They're just integers. Okay, so that's the first thing. Let's talk about some of this code. So here is relation.h. Again, every relation, it's one piece of data, like the thing that's being related, is a set of pairs. A set of pairs of ints. So every pair xy in this set of elements is saying that x is related to y in that order. X, R, Y, if our relation is called R. Okay? And so here's what we'd like to be able to do with our relations. We'd like to say, like, all right, we'd like to build our relations, or the constructor, of course, will initialize the elements. And then here's all the kinds of things that we'd like to ask about our relations. Is x related to y? That's kind of a helper function. You'll just look inside of your elements. Is related to left and is related to right are some helper functions. It's like is related to left finds all of given an x. It finds all the things that are related to x on the left. So all the y's such that y are x is true for your given x. Is related to right is the same idea. So like given an x, what are all the things that are related to x on the right? So all the y's such that x are y is true about our particular relation. And then here are a bunch of ideas that you can check about each relation, because you can just go through all the elements and make sure it all works out, right? So is this a function? You know what it means to not be a function, right? Make sure it's well defined. Is it injective? So this will return true if it's an injective function, okay? Sadly, unless we save the codomain, we can't check for surjectivity. We can't say that it's an onto function, but we can check that it's one-to-one. So that's injective. And then here are some other ones. Return true if it's a symmetric relation. Is symmetric, I think you can kind of see, given my example, right, how you might go and check for that. Is my relation symmetric? Maybe using your is related to helper function. Is transitive, as usual, will return true if your relation is transitive. Again, you can't check for reflexivity because you don't know what the domain is, unless you save what that is. Unfortunately, we can't do it. So we'll just check for symmetricity and transitivity. So that's the kinds of things we'd like to do to our relations, again defined as sets of ordered pairs. That's what it means to be a relation. And you're going to implement all this stuff in relation.cpp, okay? So I've given you the constructor. The rest of these are for you, all right? Is related to is, of course, not correct right now. It's just saying that everything is related to everything else. But you need to look through your elements. Look through your elements member variable and see if x is related to y, or x is on the left and y is on the right. That's the order is very important. So you just look through your elements and see if that's true. All right. So that's that idea. Let's see here. Yeah, let me give you some examples about some of these, like is related to left, is related to right, is function, is symmetric. So let's use our examples from before. Let me see if I can copy them as good as I can. Let me steal these guys and put them here. And so here's the example. Let me give you an example of is related to left, what it's supposed to do. If you have your relation and it's like, let's see here. Let's say we're doing it on R2 or something. If you say R2 dot is related to left, and you give some elements, let's say we give 5, what it needs to do is it needs to compute, given that relation, all of the y's such that y is related to on the left of 5. So it's like all the y are 5s that exist inside of your relation, all of the elements. So just look through every element, every pair, and that's what you'll notice. So what are all the things that are related to 5 where that thing is on the left, all right? So it looks like 5 is, which means that 5 is the thing on the right, all right? So here's the thing where 5 is on the right, here's the thing where 5 is on the right. So all the things related to on the left of 5 are 6 and 2. You see that? That's what you're going to be computing. And so you're going to give back a set of all the things that are related. And that I do believe that is the type. Yeah, you're going to give back a set of all of the labels, which are just integers of what's related. Okay? So that's is related to left. I think you can imagine is related to right is very similar. Okay? So that's that one. Is function, you're going to check that your relation is a function. So when you have a relation that's supposed to represent a function, if you have x related to y, that's saying that your function f of x is going to be set to y. X on the left is the input, y on the right is the output. Okay? So to make sure it's a function, you have to make sure that for every x, everything on the left, there is exactly one thing that it's mapping to. It can't go 2 places at once. It's a function, right? So R1, for example, dot is function. You're going to make sure like there's no 1 going to 2 and 4 at the same time. And so it should give back, this will give back true for R1, where R1 is this, because there's only one value being mapped to for all those elements. You're just going to assume that this is everybody in the domain. Nobody's being missed. All right, so that's is function. I believe is function will work for R2, but it's a bit weird looking. It's fine. Let's not go there. Likewise, R1 dot is injective is also true. I'll just give a bunch of these examples, I guess. That's also true because this is an injective function, isn't it? What does that mean? Well, again, you just make sure that no two x values share the same y value. So if I get like rid of this one and say that 3, that 1 maps to 6, now I have 1 mapping to 6 as well as 3 mapping to 6, and now it's no longer 1-to-1. But and 1-to-1 is the same as injective. Okay? But right now it's injective. Every different value in the domain is going somewhere else, to different places. That's injectivity. Let's see here. Yeah, so that's what you're gonna check for, and then R1 dot is symmetric though. You can treat a function as a relation. Is symmetric. Is going to compute, is this a symmetric relation? If you have an arrow this way, do I always have an arrow this way? Of course not. So that's false for R1, but it's true for R2. If you say R2 dot is symmetric, then that should give back true, of course. Because it is a symmetric relation. Every time you have 1, 2, you do have 2, 1. And so kind of think about how you'll check that. You're going to have to iterate through the elements, essentially. That's symmetric, is transitive, very similar. Okay, that's the idea there. And these were why we had 2 and 6 for is related to left. I think that's everything that I wanted to draw. Please yell at me if you have any questions about that stuff. Let's see here. For is transitive, you're going to have to iterate through every element in this guy, in your set of elements. But you're going to have to iterate through every pair of things being related, I guess. So the easiest way, I think, to implement this is with a doubly nested loop. So you're going to have to like try every pair of things, and if they correspond with their midpoint, you have to then go and make sure that there's an arrow in that direction. So that's transitivity. Like, I have this one and then this one, they correspond on the 2 in the middle. I better have a 1 to 5. Go and check that now. That's how you check for transitivity. You're going to have to try every pair of arrows. Try that pair. If they correspond, do something. This pair, they don't correspond, so there's nothing to check. But when they overlap like this, you better make sure that that transitive thing is there. That's how you check for transitivity. So every time you see A related to B and B related to C, where the B's are the same, then you have to make sure you see A related to C. That's what it means to be transitive. Okay? So that is essentially your lab. It's not meant to be a difficult one. But you're going to have to think about how to compute these properties of your relations. And so I've given you a few tests to make sure that it's going to work. You don't have to write any of your own. Just get my tests working. Here's a relation that's an injective function, so it's making sure that like it gives back, yes, it is a function. Yes, it is injective. A non-injective function, a symmetric and transitive relation. And I really encourage you to draw these out. Draw out my tests to understand exactly why, yes, this is symmetric, yes, this is transitive. How might I go about checking that? Okay? That's the goal. It's also checking is related to left, is related to right. So a bunch of things. Symmetric but not transitive, transitive but not symmetric, a relation that's not symmetric or transitive at all. So a few different examples, and it's run in your code. So that's the test. As usual, you'll use a makefile to compile it. And run it, get all the tests passing, and that is your lab. All right. So plenty of time to work on this one. Should be a nice easy one in between the hard ones. So yeah, the only thing that you're touching is relation.cpp, and so that's the one file you're turning in. Okay. So please yell at me if you have any questions about any of this. But that, I believe, is everything that I wanted to tell you about your lab 4. So good luck, and I will see you next time.